So in the last example, we looked at a function that was a little contrived, right? I picked some numbers carefully so it came out easy. In this example, we're going to kind of go the other way. We're going to look at a function that looks pretty simple. I mean, y equals x squared. It's the most basic of parabolas. And we're going to see how, and this is often the case with this particular formula, it gets kind of messy pretty fast. So be forewarned. All right, this is going to turn into one of those trigonometric integrals. Okay, so those get a little long, so just don't be surprised when it takes quite a few steps for us to get to the result. So where are we going to start? Well, we need the derivative, right? If y equals x squared, then y prime equals 2x, which is continuous, right? So we've met the requirements to use our formula here. So I'm going to do a substitution. I'm going to put 2x in there for f prime, and this becomes the integral from 0 to 3 of the square root of 1 plus 4x squared. Well, hopefully you remember from the last chapter, this is something that we're going to handle trigonometrically. So I'm going to do the substitution. X equals 1/2 tangent theta, which means dx equals 1/2 secant squared theta d theta. All right, so if I make those two substitutions, the integral becomes the integral from 0 to 3 of the square root of 1 plus tangent squared theta times 1/2 secant squared theta d theta. And I know I'm just going to offend some of my colleagues here, but I'm just going to leave that 0 and 3 in there for the time being as the limits of integration. Yes, we are eventually going to have to switch them out for the corresponding values of theta, but I'm going to just put that off till down the road. All right, so looking at this, the square root of 1 plus tangent squared theta. 1 plus tangent squared theta is secant theta, and, is secant squared theta. The square root of that is just secant theta, so we can get that nice substitution there. And this whole thing becomes 1/2 integral from 0 to 3 secant cubed theta d theta. Okay, not really going to try to integrate that directly. What I'm going to do here, I'm going to fall back on one of the reduction formulas that we talked about again back in the last chapter. And if we apply that here, this becomes 1/2 times the quantity. It's secant to the 3 minus 2 power theta, tangent theta divided by 2. And I've got there's no longer an integral there, right? So I've replaced that with evaluated from 0 to 3, plus 3 minus 2 over 3 minus 1, integral 0 to 3 of secant to the 3 minus 2 power theta d theta. So that's one of our reduction formulas. Now, if I just do some simplifying here, I'm going to simplify the 3 minus 2s. I'm going to simplify the fraction. This becomes 1/2 secant theta tangent theta over 2, evaluated from 0 to 3, plus 1/2 the integral from 0 to 3 of secant theta d theta. And that's an integral that we've seen before. So the integral of secant theta is the log, natural log, absolute value secant theta plus tangent theta. I pulled the two 1/2s out, right? 1/2 times that 1/2, that's where the 1/4 is coming from. And now the integrals are gone. So this whole thing is just evaluated from 0 to 3. Okay, so now I've pushed that 0 to 3 as far as I can. It's time to do the actual substitution of those numbers. So I'm going to have to find the equivalent theta values. So remember our initial substitution was x equals 1/2 tangent theta. Okay, so when x equals 0, we get 0 equals 1/2 tangent theta, which is nice. That's the tangent of theta equals 0, and the tangent is 0 when theta is equal to 0. So that one actually doesn't change. On the other side, when I put 3 in for x, I get 3 equals 1/2 tangent theta, multiply both sides by 2. Tangent of theta equals 6, which means tangent of theta, which means theta is the inverse tangent of 6. Yeah, okay. That part's not so nice. So now let's go back to where we left off on the last line on the previous slide. This is the exact same thing. All I did was I replaced the 0 and 3 in the evaluation part to 0 and inverse tangent of 6. And now I'm going to do the substitution, and this looks like it turns into an absolutely enormous disaster. But it's going to get better. All right? It's going to get better. Here's the thing. The tangent of the inverse tangent of 6 is 6. And that appears twice in the left-hand part. So those are just going to kind of turn into reasonably nice numbers. And on the subtraction part, I'm going to go and put it up here. Secant of 0 is 1, and the tangent of 0 is 0. So you see that? Yeah, that's not so bad. This whole part here is 1 times 0 plus the log of 1, which is just 0. Right? So this whole bit here just becomes 0. Right? That whole subtraction part is going to go away. Okay, and that leaves us with this expression. And now, yeah, okay, now we're going to have to deal with that secant of the inverse tangent. And to do that, I'm going to go back to our value here, right? I'm going to let theta equal the inverse tangent of 6, which means the tangent of theta is equal to 6. Okay, so let's draw a triangle, right triangle with theta filled in down there. Because the tangent of theta is 6, the opposite side has to be 6, and the adjacent side has to be 1. And if we apply the Pythagorean theorem, the hypotenuse is going to be the square root of 37, which means that the secant of this angle is 1 over the cosine. So it's the square root of 37 over 1, which is just square root of 37. Okay, one last substitution then. The secant of the inverse tangent of 6 is going to get replaced both times with the square root of 37, and we get this. The arc length is 1/4 times 6 square roots of 37 plus the natural log of the square root of 37 plus 6. And believe it or not, that is it. Right? That's as simplified as I can make this thing. So that's going to be our final answer. So first, if you made it all the way through to this point, congratulations. That one was a bit of a hairy mess. But you need to be prepared for that. Right? You're really getting to the point in your math education where things aren't always going to come out to 6 or pi or some really nice number. Sometimes you really do have to just kind of crank away at these things and accept that the final answer is going to be a little weird looking. Right? That kind of thing does happen. So in the next lecture, we're actually going to derive yet another formula. Spend some time talking about volume, right? 3 dimensions. Then in this series, we went down to 1 dimension, talk about arc length. In the next series, we're going to kind of split the difference and go to 2 dimensions. Right? We're going to talk about how we can use the integration techniques we've learned to find the surface area of a solid of revolution.